See two pictures up on the board right now. One is the logo of the Houston Astros, who are a baseball team who are 8-2 in the last 10 games. That's pretty good, right? 8 wins, 2 losses in the last 10 games. We also see a picture of a train moving down the tracks. What do these two things, the Houston Astros, who are 8-2 over the last 10 games, the best team in Major League Baseball over the last 10 games, and this train moving down the tracks, what do they have in common? I'm thinking one word, but if you think of something else, that's okay. Yeah, they both have momentum, right? They both have momentum. Now, one of these is a physical momentum, right? Like we have this intuitive notion as to what momentum is physically, right? We don't necessarily know a definition for it, but we have some sort of notion as to what momentum is. And we certainly have a notion as to what psychological momentum is, right? Clearly different, but somewhat the same. Psychologically, physically, the Houston Astros, this train, are both hard to, what's the word I'm looking for? Stop. They're both hard to stop. Yeah. Now, why is this hard, the Houston Astros hard to stop? Because, like, they're on a roll. Psychologically, like, you go up against a team that's 8-2, and it's like, oh, man, like, we're in tough here because they're playing really, really well right now. It's hard to stop a team that is psychologically on a roll. But what we're going to focus on in Physics 30 is not psychological momentum, but more physical momentum, real momentum. What makes this train hard to stop? I'll give you a hint. There's 2 factors that make this train hard to stop. What's one of them? Mass. Yeah, the train is heavy. That's why it's hard to stop. You got a butterfly going down the tracks. You got a train going down the tracks. Clearly, the train is harder to stop than the butterfly is, right? Because it's heavier. Heavy things have more momentum because they are harder to stop. What else affects the momentum of an object? What else affects how hard it is to stop something? The speed, or technically it's the velocity because it includes direction, but yeah, how fast it's moving. The heavier it is, the faster it's moving, the harder it is to stop. We're going to define momentum loosely as how hard it is to stop something. That's not the technical definition, but it's the way we understand momentum. It's the way we think of it. That leads us very nicely into the real definition, which is what causes something to be hard to stop. And that is, as you guys just told me a minute ago, mass and velocity. So we understand momentum as how hard it is to stop something. We define it as the product of an object's mass and velocity. Jacob, vector or scalar? Vector or scalar, what do you think? Yeah, it's a vector, right? It's mass and velocity. Velocity is a vector, so momentum's got to be a vector as well. The vector nature of momentum is pretty easy, really. If the velocity is to the west, then the momentum is to the west. If the velocity is south, then the momentum is to the south. No tricks there. The momentum is just the same direction as the velocity. Now, there is another term that's often associated with momentum. You've heard it before in Physics 20. It starts with an I. Yeah, inertia. Who said that? Parker? Yeah. Do you remember what inertia is, Parker? Yes? Yeah, an object, it's that first law, right? Yeah, exactly. It's the tendency to resist a change in motion. Object at rest wants to stay at rest. Object that's in motion wants to stay in motion in a straight line at a constant speed. So the inertia is a tendency of an object not to keep going, the tendency of an object to keep doing what it's doing. If it's at rest, it wants to stay there. If it's moving, it wants to stay there. It's a tendency to resist any kind of change in motion. There's a subtle difference there between inertia and momentum. Momentum, how hard it is specifically to stop something. Inertia could be how hard it is to stop something as well, but it's also how hard it is to speed up something or to start something or change the direction or change the speed in any way. How hard it is to change motion in general. Inertia is dependent upon one thing. What would it be? What would it be? Yeah, Ben? Yeah, good. It's the mass, right? So momentum depends upon mass and velocity, whereas inertia depends only on mass. Okay, we see two trains up on the board right now. One of them's at rest at a station. One of them's in motion on the track. I want to compare the inertia of both of these trains, and I want to compare the momenta of both of these trains. First train at rest in a station. Does it have inertia? Does it? Yeah, it does. How come? Because it has mass. Good. It has inertia because it has mass. What about the train moving down the tracks? Does it have inertia? Danny? Yeah, absolutely. How come? Good, because it has mass. Is it ever possible for the moving train to have more inertia than the stationary train? Can the moving train have more inertia than the stationary train? Can it? Yes, it can. Is it possible for the stationary train to have more inertia than the moving train? Yes, it can. Why can the stationary train have more inertia, or why can the moving train have more inertia? Yep. Difference in mass. If the stationary train is heavier, it's got more inertia. If the stationary train is lighter, it's got less inertia. Does that make sense? Depends only on mass, not on velocity. What about momentum? Does the train at rest at the station have momentum? No. How come? Why not? Because it's not moving. It doesn't matter how much mass it has. It might have all the inertia in the world. It might be hard to change the motion of that train. It doesn't matter. It doesn't have any momentum. Good. What about the train that's moving down the track? Does it have momentum? Absolutely. Is it ever possible for the train that's at rest to have more momentum than the moving train? How can a train that's at rest have more momentum than a train that's moving? A train that's at rest with zero momentum cannot have more momentum than a train that's moving. Okay, make sense? You understand the difference here? Okay, listen, we're going to be focusing almost entirely in this unit on momentum. I just want you to understand the difference between momentum and inertia. I'm going to ask you right now to flip to your data sheets, the little booklet that I handed out at the beginning of class here. Third page, bottom left-hand corner. You can see a whole bunch of equations on this page. There will be no red circles, like you see up on the board right now, but that's the one that I want you to look at, the one that's circled in red on the board. It says P is equal to M times V. What do you think M stands for? M stands for what? Mass. Yeah, mass. Good. And what are the units for mass? Kilograms. How many people take chemistry right now? Chemistry, Ben, what units do you use in chemistry usually for mass? Usually it's grams. Chemistry, right? Usually grams. Let's not get those mixed up, okay? If you take chemistry, stick with grams usually. If you take physics, we're going to always use kilograms, okay? What does V stand for? Velocity, right? Not speed, but velocity. And the units for velocity would be meters per second. Good. Sometimes we see velocity in kilometers per hour, right? We got to convert that to meters per second. We'll go through a couple examples of conversions in just a moment. What do you think P stands for? Little p. Big P would be power. This is a little p with an arrow over top of it, meaning it's a vector. Stands for momentum, right? Yeah, it stands for momentum. JC, go ahead and ask me why little p is a symbol for momentum. Because it seems kind of weird, right? P for momentum? Ask me why. I don't know. I don't know. It just is. Okay, you got to remember that little p is a symbol for momentum. What are the units? Oh, you guys can all tell me this right now. It's staring you right in the face, literally. What are the units for mass? What are the units for velocity? And what's mass times velocity for units? How about kilograms times meters per second? Does that make sense? Mass times velocity, kilograms times meters per second. That's it. Okay, that's it. let's do a couple conversions here just to make sure you're okay with those. Let's say, for instance, I don't know, let's say, you know what? I'm going to make some pasta sauce when I go home tonight. Use some ground beef, 1 pound of ground beef, 454 grams of ground beef. But I don't like being in grams because I don't like chemistry. So I'm going to convert to kilograms because that's what we use in physics. I want to convert 454 grams to kilograms. How do I do it? How do I do it? Yeah, you're right. Check your data sheet, page 2. You see this little title that says prefixes used with SI units. And you see a kilo is 10 to the 3. A kilo is 1,000. So we're going to take 454, we're going to divide it by 1,000, and we're going to get 0.454 kilograms. So Jacob, you're right. You divide by 1,000. What if you had looked at that and said, oh, I think I multiply by 1,000? If you multiply 454 by 1,000, you get 454,000, right? Would it make any sense for me to cook 454,000 kilograms of beef to make pasta sauce tonight? Like, listen, it's okay if you multiply when you're supposed to divide. Just make sure you look at your answer and see if it makes sense, right? If you did it right, it'll make sense. If you did it wrong, it won't make sense. Just fix it, okay? What about this one? What about 90 kilometers per hour? We want to convert that to meters per second. Anyone? Yeah. Well, I'll tell you what. You're using that shortcut, eh? I never taught that shortcut to my Physics 20 students. Wow. Yeah, I know. Thinking, isn't he mean? Here's the way I did it, Physics 20. 90 kilometers is 90,000 meters, right? Agreed? 1 hour on the bottom is 3,600 seconds. Divide 90,000 by 3,600 meters per second, we end up getting 25 meters per second. But what we can do, take a little shortcut, not multiply by 3.6, but divide by 3.6, and it gives us 25. Okay, so my students last year for Physics 20 are now allowed to use the shortcut. Divide by 3.6. Now, if you did multiply by 3.6, I told you it's okay to get that wrong, right? Take your calculator right now. Do you have your calculator there? Take 90 and multiply it by 3.6. Let's see what you get. I'm not sure what it is off the top of my head. 270, what's 6? I'm going to say, what is it? 324. 324 meters per second? So a car is traveling down the road at 90 kilometers per hour. Does 324 meters in 1 second, like 3.5 football fields, does that seem reasonable? No, right? It's okay to be wrong. Just make sure you check to see if it's reasonable, right? That's not, so it must be divide by 3.6. Okay? Good? Okay, good. We're going to do an example here. It's the first example that you see in the booklet that I handed to you earlier. At the top of the page, it says C12 example problems. What does that C12 mean? I also gave you a book at the beginning of the class that says Physics 30 and 13 pages. If you flip over to the second page, it says Concept 12 is momentum. So these examples go with Concept 12 on the Physics 30 and 13 pages. The reason we skip the first 11 topics is because they just kind of go with the other ones. As we do the other ones, we'll kind of cover the first 11 topics. So example number 1 for Concept 12. First thing you want to do, pull out the red pen, pull out the highlighter, pull out the purple pen, whatever it is that you have that's different than what you usually write with, and draw attention to this, and this, and this. Why did I do that? Why did I circle those things? Not because they're givens, but because, yeah, like I wanted to draw attention to to whatever I thought might lead me to a silly mistake. We all make silly mistakes. If we do this, when we read a question, we're less likely to make a silly mistake. Listen, I'm going to tell you that when you get your diploma exam, you are most likely going to make mistakes. That's okay. It's fine to make mistakes. If you're going to make a mistake, though, make it a good one. Like, make it a gooder. Don't make some mistake because you forgot to convert 145 grams to kilograms. That's a waste of a mistake. Okay? Like, if you're going to make a mistake, like, you might as well just butcher the question. Don't make some mistake because some silly mistake because you forgot to convert units, okay? If you draw attention to things like this, we're less likely to make that mistake. Okay, let's write down some givens here. We have our mass of 145 grams. We're going to divide that by 1,000. We get 0.145 kilograms. My velocity is 90 divided by 3.6, which is 25.0 meters per second. And we're looking for the momentum. Hey, I'm missing one small thing. What is it? One small thing. Yeah. Yeah. Listen, I circled west so I wouldn't forget that it was west, right? It's an easy thing. If it's east, like, you're good usually, right? But if it's west, you want to remember to make the V a negative value. Okay, this is an easy question right now, right? Let's say P is equal to M times V. M is 0.145 kilograms. V is 25 meters per second, negative 25.0 meters per second. Multiply these together, we get negative 3.63. Remember the units? Remember the units? Tim, what were the units for momentum? Yeah, good. Kilograms times meters per second. Good. Notice I made my final answer 3 digits because this is 3 and this is 3. Okay, now that we're done that, I'd like you to take a look at the worksheet that I gave you at the beginning of class, worksheet number 1, and take a look at questions 1 to 4 only on worksheet number 1. Questions 1 to 4. I'll give you a chance to work on those in class. Take a look at them, and then we'll move on and do one more example after that. 1 to 4. Let's do one more example now that you're done with those questions here. Example number 2 says a 1.5 kilogram object falls from rest from a height of 14 meters down to the ground level. What's the momentum of the object as it hits the ground? What makes this question different than the last question that we saw? It's falling, yeah. So the last question didn't have any kind of acceleration taking place. This one does, right? The other thing is that we knew what the velocity was in the last question. We were told in the last example that the velocity was 90 kilometers per hour to the west, right? What's the velocity here? Yeah, we have to find it. We wouldn't do it that way, no. But we do have to find it, yeah. So let's do that. Let's write down some givens. Let's find the final velocity, and then let's find the final momentum from that. M is 1.5 kilograms. Tell me what 14 meters is. What is that? Is that A? Is that D? Is that V? What is that? Yeah. You could call it H. Yeah, the initial height. Yeah, absolutely. Or we could also call it, I'm going to call it the displacement. Does that make sense, JC? Now, I'm actually going to make it negative 14. How come I did that? Because it's down, right. It started at this height 14 meters above. It landed on the ground. It landed 14 meters below where it started. So we're going to make that negative 14. Is there anything else that we have here if we read between the lines? Any other pieces of data? There's a couple things that I'm thinking of. What's one of them? Yes, the acceleration is negative 9.81 meters per second squared. Good. Good. What else do we have if we read between the lines a little bit here? Yep, Ben? Yes, what is it? Good. VI is 0 meters per second. Now, in a question like this, VI won't necessarily be 0 meters per second, but because it specifically says here it falls from rest, then VI is 0. If it was moving at 5 meters per second before, like when it was thrown at 5 meters per second at a height of 14 meters, then we would say VI is 14, right? Okay, we want to find the final momentum here. In order to find the final momentum as it strikes the ground, we're going to say m times the final velocity. Mass is easy, 1.5. What's the final velocity equal to? We don't know. So somebody said, Parker, I think it was, said earlier on that we got to find that, right? Any ideas how we might find that? A couple different ways. One way that most people lean towards. I love seeing what I just saw from a few of you guys. Okay, the difference between the beginning of Physics 20 and Physics 30. I asked that question in Physics 20. People are like, I don't know. Physics 30, people are opening up their data sheets because they might not know how to answer the question, but they at least know where to look, right? They at least know where to look for it. What do you think we're going to do? Janae, which one would you use? Good. Exactly. It's not the only option, but I think it's the easiest option. VF squared is equal to VI squared plus 2AD. VI is 0. That's good news because it makes the equation a little bit easier to rearrange. VF is the square root of 2 times A times D. Square root of 2 times neg 9.81 times the displacement of neg 14. When we do this, we end up getting a VF that is equal to 16.5735. Okay, pay really close attention here. What have I just solved for? 16.5735. What is that? The final what? No. Final speed. Good. Final speed. Because the little v doesn't have the arrow sign over, right? Final speed. What do I need to plug into that equation? Yeah, I need final velocity, right? Which way is it moving? If the ball falls downward, which way is it moving when it hits the ground? Down. Okay, so when we sub it into this equation, P is equal to m times v, let's just add a negative to it. 1.5 times negative 16.5735. See what I've done there? Okay, we solve for final speed. That's okay. We need velocity. We're smart enough to recognize that it's moving downward when it hits the ground. So we'll just add a negative to it to make it velocity. We do the math on this one. Works out to be negative 25 kilograms meters per second. Notice I went 2 digits here, 25. This is 3 digits, right? But this is only 2. So final answer should be 2 digits. Does that make sense? Now what I'd like you to do is just finish up that worksheet, questions 5 through 8. Okay, you have about 10 minutes in class. If you finish them, great. You have no homework. If you don't finish them, then I'll ask you to finish those up for homework for tomorrow, please.